Hello and welcome to episode number 16 of CS350 Online. I'm your host as always, Leslie Eisted, and in today's episode we're actually going to start a new topic, which is the topic of scheduling. Now first I want to apologize for starting so late today. Had to get the ice cream put away when the groceries came in, so nobody likes melted ice cream, right? Couple things though about today. So first off, if you're following along with the readings, and again, I can't stress enough that these are absolutely not required, but if you are following along with the readings, this would be the scheduling MLFQ and multiple CPUs episodes or sections of the textbook that you might want to read. Again, it's totally up to you. And the other thing I want to remind you of is don't forget to actually do the quizzes on Learn, and don't forget about those reading assignments, because the reading assignments are only open for a very short period of time, I think like a week or two. Actually, I think it's more like a week to 10 days. And I would recommend reading the paper a couple times before you attempt the quiz, simply because you don't want to have to be trying to read the paper for the first time while you're writing the quiz. So read it a few times before you actually go to attempt the quiz, and then go and attempt it. I don't find the papers that bad. They're actually fairly straightforward. The first one is a scheduling paper, which is a topic. The scheduling algorithm is called the lottery scheduler, which I think is actually a really cool scheduling algorithm. And it's not included in these slides here, which is why we thought it'd be fun to do a reading assignment on it. Here, read about this new thing. Yeah, lottery scheduling isn't new, but it's cool. And then the second reading assignment is to do a file system, and it's the log structured file system. And again, both papers are very approachable, I think, so hopefully that will be interesting for some of you. All right, so let's move on to our OS of the day. There it is, the lovely OS of the day. Okay, so today's operating system is one that I actually think a large number of you have probably heard of, and that is DOS. And DOS stands for Disk Operating System. And what's interesting is this isn't actually the first operating system to actually be called DOS. There was actually an older operating system for PDP that was called DOS as well, but very different. So DOS was released in 1981, and it was released with IBM's first personal computer, which was the 1981 IBM PC, not PC-AT, not PC-XT, just the PC. And the model number, of course, was 5150, which you may have seen. A lot of computers end up having that model number, 5150, and it's actually almost an homage to this original PC, which was the original 5150. And I think, if memory serves me, so it had an 8086 or an 8088 processor. Don't quite remember. But the rating on it, so we're used to computers now that have, gigahertz in terms of their computational power. Not this one. So this one, you'd think I'd remember considering I had one. This one had a processor that I think was 4.77 megahertz. So your watch has more computation power than this thing had. And yeah, it was the Intel 8088 processor that was in it. And the default amount of RAM that you got was either 16 kilobytes or 64 kilobytes. Now, what was interesting is I actually got my IBM PC secondhand, and the person who I got it from had actually put an expansion board in it from Quad RAM. And that gave me 256 kilobytes of RAM, which was, that was pretty cool. But the Quad RAM board, the expansion board, was actually bigger than the case. Like, it didn't quite fit in the case properly. So it would actually, and this was intended, it hung out the back of the case a little bit. I mean, that was always the design, but it's very odd, because when you think of RAM today, you're thinking about the little DIMMs, and they're just little sticks. But no, in like the 80s, this thing was huge. I mean, the graphics card in it was huge as well, and I actually had a Hercules graphics card, but I didn't have color monitor, so it was kind of pointless. All right, so what happened, though, with DOS? And DOS is actually an interesting story. So DOS was actually wasn't supposed to be the operating system that was released with this computer. IBM was actually developing their own operating system, called CPM. And the problem was when the hardware was ready, the operating system wasn't. And they didn't want to delay the hardware just to wait for the operating system to become available. So what they decided to do was when they saw they weren't going to make the deadline for CPM, they actually approached Microsoft and said, hey, Microsoft, we need an operating system that can do these things. So they asked Microsoft to develop an OS for them. And Microsoft developed it by buying it from somebody else and then modifying it. So they actually bought DOS from Seattle Computer Products. And then they modified that. And then Microsoft sold it back to IBM, and that became what's known as PC DOS, so personal computer DOS. And that is the operating system that shipped in a really loose sense of the word, for the 1981 IBM PC. And that's the DOS that I used when I was younger. Now, what's interesting is Microsoft turned around and they made their own variation of DOS, which they called MS-DOS. And they released that one as well. And for some reason, there are also a whole bunch of other variations of DOS kicking around. And I remember when I got the IBM, and that was my first computer that actually worked, it actually, it came with these shoe boxes full of floppy disks. And I found all these different DOSes in there. And I was like, what is going on? So there's a whole bunch of variations of DOS. There's 86 DOS. There's Dr. DOS, and there's Double DOS, and there's a whole bunch of other ones. And I had these different variations here. I couldn't tell you what they were for because, I was a lot younger when I was playing around with it, and I didn't really know what any of the differences were. But yeah, there's lots of variations on DOS. Now, what is DOS as an operating system? So it's a very, very basic OS. It has no multitasking. It has no desktop GUI or any mouse controls or anything like that. It has a very, very basic file system, which we will learn a bit more about when we talk about file systems. It's called the FAT file systems. And it uses this 8.3 file name format, which you might remember vaguely. I certainly remember it. Your first part of your file name can only be up to 8 characters, and your extension can only be 3 characters. So if you're downloading stuff on BitTorrent, yeah, it doesn't work because that's like a 256 character name, and you're only allowed to have 8. So it's always getting creative with naming your files. So the interface for DOS, of course, was command line, very, very simple. It was nothing sophisticated like a terminal on a Linux-based or Unix-based computer. It would let you do things like open files, and by open files, I mean run programs, so you could load programs, and you could load a basic editor. You could not, I say basic editor, and you're probably thinking, oh, like Nano or VI. No, I mean BASIC, the programming language. And you could do things with the file system that were very simple, like you could make directories, you could navigate the directory structure, you could remove files and things like that. But you couldn't really do much with it. It also supported some very basic scripting called batch files, which you might be familiar with. They're the .bat files on any Microsoft product. But back then, the support for those was actually quite limited. Some other interesting features, because this was such a limited tool, they weren't worried about things like security, and they weren't worried about compatibility so much. And so they had very limited memory support. So I believe it's 16-bit addressing and direct hardware access. Yeah, and actually, if you've noticed, so it's kind of weird, you might have thought, that the very end of each of these videos, I'm showing you a video game. But actually, the reason why I'm showing you those video games is because they kind of have interesting tie-ins to operating systems. Because the ones I'm choosing tend to be old DOS games or self-bootable games. And what's interesting is that in the when we think of games and when we go into a store to buy a PC game, I don't think, does anybody even do that anymore? I think if you want a game now, and if it's on Steam or whatever it is, you just go on Steam and you just buy it, and it downloads right away. And then if there's a patch, it just gets patched silently and you don't even know. But a long time ago, when games were DOS-based or self-bootable, before people used DOS, because not everybody bought DOS, it was a lot more complicated to actually run video games. So for example, some of the games I've shown you actually have you pick your graphics card from a list, and it's because the game has hard-coded driver support into it for only like 3 specific kinds of graphics cards. And if you have something else, then the game isn't guaranteed to work. And the same is true for things like joysticks and other kinds of peripherals, sound cards. Trying to get games to work in the 80s and 90s wasn't always trivial. And when you went into like EB Games back then, and because we didn't do things over the internet back then, you would actually have to really carefully look at the side of the box to make sure that your computer met those standards. And one of the things that would often happen is the games would come with a bunch of built-in things that you would have to install. Like I remember when I bought Final Fantasy VII. Actually, no, I didn't buy it. My friend bought it. I didn't have a computer that could run Final Fantasy VII at that time, but my friend did. So when she bought it, and we took it back to her house, and we go to install it, before you can even install the game, there's like 20 drivers you had to pre-install, just so that it was guaranteeing that your computer was compatible with the game. And even then, there was no guarantee. So things have really, really changed, and a lot of it ties into operating systems and driver support. So yeah, it's kind of interesting. But yeah, because DOS had direct hardware access, one of the issues that came up a lot was driver support. And the driver support for games actually had to be built into the game itself to ensure that you could actually play it. So, yeah. And yes, I have had these problems before. So I remember my first 486 I bought, which I had to buy used, but that's another story. But like I got the secondhand 486, and the sound card was an unusual sound card. And to be fair, so was the CPU. So back in the 80s and 90s, there were knockoff CPU brands. So there's knockoff Intel brands, and one of them was a brand called Cyrix. So I actually had a Cyrix 486 processor. And so that actually made running DOS games even harder because they weren't designed for that particular knockoff CPU. And I ended up with a weird combination of a CPU and a sound card. And so all of the games I would buy, I didn't have any sound because DOS did not... There was no driver support for it through DOS. So it's, yeah. Very, very simple operating system. Now, a lot of you have probably seen DOS because even today, if you open up Windows, and I'm not in Windows, this computer I'm using right here is a lovely Kubuntu machine. But if you do open up Windows, you can open CMD, so command, which gives you a DOS prompt, but it's not real DOS. It's an emulated DOS, and it's actually far more capable than DOS ever was. Windows has not been based on DOS since Windows 2000. So the consumer Windows versions 2000 and up are all not based on DOS. They are giving you a command prompt just for almost legacy reasons, I want to say. All right, that's like a long rant. I could talk for a long time about DOS and some of the quirks of it, but we don't have that much time. All right, then. So, and yes, don't worry, I will have more fun DOS games for you at the end of each episode. Some of them are favorites, and some of them are classics, and some of them are ones that have interesting quirks related to OS. So what I want to do now then is we're all done with virtual memory. So now I want to switch over and let's actually just talk about our new topic today. Have to excuse me. I am still... This is only the second time I've live streamed from this machine. So it's going to take some getting used to. Don't want that one anymore. Where'd the other one go? Just open a new one. There we go. All right. So today what I want to talk about is actually one of my favorite topics for operating systems. In fact, if you had to ask what is my favorite topics or favorite parts of this course, my favorite parts of the course are from scheduling to the end. So scheduling, devices, file systems. Yeah, that's my favorite part of the course. So one of the topics that we've completely brushed aside throughout this entire course is when there's a context switch, how do you choose which thread actually goes next? We've completely ignored how that actually works. We've just assumed it works out and it's magic and we have no control over it. But there's actually a pretty big topic here in how do you actually choose the thread that goes next? Because obviously we want there to be some kind of logic behind how we choose the next thread. So first off, we're going to just talk about, we're going to go back in time to like the 1950s and talk about this. And instead of calling things threads or programs, we're going to call things jobs, because that's how everything was kind of seen back then as, as being a job that you had to schedule. And the machines that ran at that time could only really schedule one job at any time. So only one thing could run at a time. Now, if you're sitting there saying, but this isn't relevant to today's computers, how do we actually do scheduling on a multi-core system? Wait till the end of this section. We'll talk about multi-core scheduling at the very end. But for now, we're just going to talk about scheduling for a single core CPU. So just one job can run at a time. So if we're thinking back to the 1950s, there's a couple things from a theoretical perspective we have to talk about. First is we know what time each job arrives to the queue. So we're going to assume there's some pool of jobs that's like a ready pool or a ready queue or what have you. And the whole purpose of that ready queue or ready pool is it's all of the jobs that are ready but not currently running. And we know at what time each job actually shows up. We're also making the assumption that we know how long each job is going to run for. Some of you are probably sitting there, but wait a minute. Okay, we'll come back to that one in a minute, okay? Then for each job, there's a couple of different metrics we can define. We have the response time, which is how long it takes between when the job arrives and when the job actually starts to run. So how long does it take to actually start running the job that's just arrived? And then we have the turnaround time, which is the time between arrival and when the job actually finishes running. So how long does it take to actually have that job start and end? What is completion time? And then when we're trying to decide which job goes next, ideally we want to minimize one of the average of one of these things. So either we want to minimize the average response time or we want to minimize the average turnaround time, because we are wanting to keep our system as occupied as possible, and we want to make sure that things are pushing through and pushing through and pushing through as fast as possible. We don't want users to have to wait for obscene amounts of time for the jobs to actually start and finish. All right. So there's a few different strategies that we can actually use for a scheduling algorithm. Sorry, I'm just turning my tablet on here because I do want to do some writing. It's funny, it's kind of a race. So I have, you've seen me, I do all my writing using one of these Wacom tablets. And it's actually connected over Bluetooth to two of the computers sitting right here. So it's kind of a race. Which of these two machines is going to pick up the Bluetooth connection first? And the desktop, the Ubuntu, wins every time. So it's kind of funny. Anyways. So the easiest strategy that we could use to schedule our jobs is first come, first serve. So the ready pool is really just a queue, and we are going to serve the jobs in the order that they arrive. So when you arrive, you go to the back of the line, and when we want a new job, we just take from the front of the line. There's some really nice advantages to this particular method. For one, it's very simple to implement. We just need a queue, and hey, guess what? We already have one of those in OS 161. The other advantage of first come, first serve is it avoids this concept of starvation. And starvation is a bad thing when it comes to scheduling. And this is actually going to come up again when it comes to file systems as well. So starvation is the concept where you are in the ready pool and you are waiting to be scheduled to run, but for whatever reason, all of the other jobs, even jobs which are newer than you, end up running before you. And so the chances of you actually running are really small. So starvation tends to be a problem with some scheduling algorithms, as we will see, but first come, first serve, there's no starvation. You get served in the order you arrive, so there's no worries about that. So we have this little Gantt chart here. So we've got these jobs. So job 1, 2, and 3. And we're going to assume that they arrived exactly in that order. We know that those 3 jobs arrived at time 0 and their run time is 5, 8, and 3 respectively. And then at time 5, job 4 arrives and it has a runtime of 2 units. So if we actually draw out when each of these jobs run, job 1 goes first because it's at the front of the line. When it completes at time 5, so that's the time at the bottom, then job 2 runs because it's next in line. It runs for 8 units of time, and when it's completed, then job 3 runs, and then finally job 4. Now, job 4 technically arrived in between job 1 and job 2 running, but because it goes to the back of the line, it has to wait its turn. So that's first come, first served. Very simple. Now, what's interesting is OS 161 actually uses a variant of first come, first serve that actually adds in preemption. So the idea is called round robin, and this is OS 161 scheduler. It is first come, first served with preemption. So what's going to happen is we're going to assume our scheduling quantum is 2 units of time. And if a thread or if a job is still running when the timer goes off, we kick it off the CPU and it goes to the back of the line and waits its turn again. So whenever a job terminates, it leaves. When a job gets preempted, it goes to the back of the line. When a new job arrives, it goes to the back of the line. If a job yields, it goes to the back of the line. So that's generally the policy with round robin, is you go to the back of the line and you wait your turn to come around again. So you can see here on the Gantt chart how this works, but I'd like to actually draw it out, and I've got to remember the name of this program. I think that's it. So what I want to do, do we still have the pin? More actions. Oh, I've missed that so much. Sorry if you're wondering what I had missed so much. It's the ability to keep a window above others. It's one of my favorite things. Window layering, forced window layering. Okay. Oh, I'm gonna have to close this program. So there's a weird bug with this program. Yeah, I know. There was a bug with OneNote as well. But the weird bug with this one is that I actually have to restart it in order to get it to recognize the pen for some reason. Oh well. Oopsies. I'm working with a single screen now instead of 2 screens. I mean, it's kind of like I have 2 screens, but I don't. So what I've got here then is we've got our time. Oh, that's so tiny, I can't see that. Page width. Okay. Oh, there we go. Now I can read this. So we've got time here, and then this is going to be our ready queue. Okay, so what's going to happen at time 0, our ready queue has, and for each job, I'm going to write how much time it actually has left in it. So job 1 has 5 units left, job 2 has 8 units, and job 3 has 3 units. And at time 0, we are going to choose, of course, because it's at the front of the line, we choose job 1 to go. Now, at 2 units of time, job 1 was still running, but that's the length of our scheduling quantum, so now I am actually going to preempt it. So at time 2, before we choose a new thread, this is what our ready queue looks like. And you'll note that I've updated the remaining time for job 1 to subtract 2 units because that's how long it's actually run for. So at time 2, then we select job 2 to run. And it's going to run until time 4. And at time 4, this is what our queue looks like. I apologize for the somewhat messy writing. So at this time, you'll see again, we've put job 2 preempted and at the back of the line, and we've updated how much time it has to run. So it's now at 6 units. And so now select job 3 to run. Now, while job 3 is running at time 5, now this is a special one. This is not a preemption. This is just something that happens while job 3 is running. While job 3 is running, job 4 arrives. And it goes to the back of the line. Okay. And then at time 6, job 1 gets preempted, and so the queue, or job 3 gets preempted, and so our queue looks like this. Okay. And again, we're going to choose the one that's at the front of the line, which of course is going to be job 1. So job 1 finally gets its chance to run again. And it's going to run until time 8 where it gets preempted. And then we're going to run job 2. That goes to time 10. And then at time 10, we're going to choose the one, again, always the one at the front of the line. Now, job 4 doesn't get preempted. It terminates just before preemption happens. So at time 2, job 4 completely leaves the system, and we take job 3. Trying to see this tiny little dot on this big screen is kind of hard for me, I'm not gonna lie. So then we take job 3. Now job 3 terminates at time 13. And so our queue ends up looking like this. So job 3 has left the system, and so what we're going to do now is we take job 1, and then job 1 is going to terminate at time 14, and so we're left with just job 2 in our ready pool, and it's going to get selected in each of those times. So that's round robin. So it's first come, first served with preemption, and this is what OS 161 does. It's very straightforward, easy to implement, not too bad, right? Lovely. But, you know, we have these goals of minimizing the average turnaround time or minimizing the average response time. And these algorithms don't do it. I mean, these algorithms here guarantee there's no starvation. There's some other advantages. For example, if you yield, you know exactly what you do. You go to the back of the line. They're very easy to implement, but they don't minimize anything. So let's try something else then. So what if we tried to actually minimize average turnaround time? So we have this thing called shortest job first. Now, what shortest job first is we are going to look at things not in terms of what order they arrived in, but we are going to run jobs in the order of runtime. So the shortest job, the one with the lowest runtime, is always going to go first. So for shortest job first, without any kind of preemption, we look at the 3 jobs that we have in our pool. We have job 1, 5 units. Job 2 uses 8 units of time, and job 3 uses 3 units of time. Of those 3 jobs, job 3 is the shortest, so we are going to let job 3 go first. And then what happens is of job 1 and job 2, job 1 is the shortest, so we are going to let it go. And while job 1 is running, job 4 arrives into the pool. So when job 1 is done, we have to choose between job 2 and job 4. Well, obviously job 4 is shorter than job 2, even though job 4 just arrived. So job 4 gets to go, and then finally job 2 gets to go. Now, this is going to minimize average turnaround time, but this has a big starvation problem. If you are always letting the shorter job go first, then these longer jobs are always going to get pushed back. It's kind of like being in the grocery store. There's this comment, and I know maybe you haven't been in a grocery store in a really long time. I know my family's been doing curbside pickup, so I haven't actually been in a store in like almost 2 years now. Year and a half anyways. But if you were actually at a grocery store, there is this common courtesy where if the person behind you in line has fewer items than you, like let's say you've got 2 carts full of ramen noodles, and the person behind you has a loaf of bread. Courtesy dictates you let them go in front of you. But if you follow that policy, then a never-ending stream of people could show up behind you with 1 loaf of bread, 1 bag of milk, 1 case of Pepsi. And courtesy would say you have to let them go in front of you. And then what ends up happening to you is you starve to death in the grocery line with 2 carts full of food. So while this might minimize average turnaround time, it's not going to stop starvation. So starvation is completely possible. It's not to say this algorithm has never been used in reality. It's just to say it's not very practical. And there's other reasons for which this algorithm is not practical, and we'll talk about it in a minute. So there is a preemptive version of it, but there's actually several preemptive versions of it. The preemptive version we're going to talk about here is when a job arrives, you preempt the running thread, and you choose the thread to go, or the job to go next that has the shortest remaining time. So this is SRTF, shortest remaining time. So what is happening here is when a thread or a job arrives, we preempt the one that is running, and then we reselect. So there's the example here, but what I would like to do is actually draw this one out, just like we did with round robin. All right. Oopsies. So I've got my time, and instead of a ready queue, now we have a ready pool. You know, I do have to admit, so this journal program here, external, however you want to say it, it may be a little bit buggy when you start it up, but you know, when I scroll, it doesn't do the thing that OneNote did, so I can't complain about that. And it's really responsive. Like way more responsive for the pen. Anyways. So again, I'm going to write the jobs with how much time they have left because we need to keep track of that for this. So I'm just going to use this notation here. And so obviously the shortest job is going to be, shortest remaining time is job 3. So job 3 is going to go. And job 3 actually is going to complete, because no new jobs are going to arrive while it is running. So at time 3, there's my little tiny dot, I have job 1 and I have job 2 in the ready pool. And of this, the shortest remaining time is job 1, so I'm going to select it to go. And it is going to run until time 5, because at time 5, what happens is job 4 arrives. And at time 5, I can see that the job with the shortest remaining time is actually going to be job 4. And so job 4 arrives and gets to go immediately. You can see here why we are averaging or minimizing the average turnaround time, because what ends up happening in reality is most jobs are short, and they arrive a lot of the time. So they're arriving more frequently than big jobs. And so we're minimizing the turnaround time for these really, really short jobs. Uh-oh, where's my dot gone? Can't find it. So now what we want to do is now job 4 is going to run to completion because no more jobs arrive. So at time 7, we have job 1 left and we have job 2 left. And so what we're going to choose at time 7 is we're going to choose job 1. And then it's going to run for 3 units of time. So then at time 10, when it ends, all we have left is job 2. And so job 2 gets to run till the end. But you can see here how job 2 ended up still starving. So even though we've added preemption, and this is not a time-based preemption, although I can tell you that if you do the time-based preemption for this one as well, where the scheduling quantum is 2 units, you actually end up with the same result for this particular example. In any way you do it, this job here, job 2, ends up starving. And this would be especially true if jobs were continuing to arrive, which in reality, that is exactly what would happen. Now, I said that this is kind of impractical, infeasible for a number of reasons. And number one, we're not really talking about jobs, we're talking about threads here. We're talking about scheduling threads. And there's a lot of reasons why these algorithms that we've shown you so far aren't really used. I mean, first come, first serve and round robin definitely are used, and they are used by simple operating systems like OS 161. But things like shortest runtime first, not so much. Because a lot of these rely on how long the threads are going to run being known. Do you know how long the thread is going to run for? Because I don't. When I sit down at my computer and I open something like the GIMP, I don't know how long I'm going to have it open for. If I'm playing a video game and I say, okay, I'm only going to play 30 minutes of Red Alert 2. I mean, sure, you can put a timer on your desk and you can flip it, and when the timer expires, but there's always one more thing you want to do. It's like, oh, you know, I'd like to try to take out the enemy base with a bunch of, let's just use one prison tank today. That's not enough, but the point I'm trying to make is we as humans do not know how long these threads are going to run for. I mean, something like a movie, you might be like, well, I know how long the movie's runtime is, but what about pausing it? What about stopping it altogether, stopping it earlier, or pausing it and then restarting it? These are things that the computer can't predict, so we really don't know as a user how long the threads are going to run for. But furthermore, we don't know how long it's going to take to run on the computer. So I did this experiment many, many years ago in grade 8, so a long time ago. We had Commodore 64s in every classroom, and we wrote a little basic program in class to print the numbers from 1 to 1,000,000 onto the screen. That seems like a really, really simple job. And it is a simple job. Do you know how long it took? It took 12 and a half hours to print the numbers from 1 to 1,000,000 onto the screen on a Commodore 64. Okay. So that job took 12 and a half hours to run. But I could take that same program and I could write it in C or C++, and it will take a fraction of the time. Like, let's just do it right here. I need a different terminal first off, because that's a project. And I need to make this text bigger because I'm pretty blind here. So let's just samples. If you're wondering, my keyboard sounds different. It's because I have a different keyboard. I had borrowed my daughter's keyboard, but she wanted it back, so I had to get another one. So let's write a little program here. Yeah, I'm going to use C++. Because so, ooh, nice tab being 8 spaces. I love it. All right. Real simple piece of code to write here. There we go, right? Sorry, I'm so used to writing code on the Apple and it giving me grief when I compile. It's just such a relief to see GCC actually work. All right, so let's run this. Wow, that was so fast. Wait a minute, how fast was that? So it took 12 and a half hours for this program to run on the Commodore 64. That just took like a couple seconds. How many seconds though? This is an interesting problem. So there's this wonderful Unix command you can use called time, and I really recommend you use this. So I can time how long it takes to run this particular user program. And it's telling me that it took just over 1 second to run this program. So it took like 1.16 seconds to print the numbers from 1 to 1,000,000 onto the screen. Wow, talk about performance improvements between a Commodore 64 and a Ryzen 9. So, okay, is it the same amount of time every time I run it? Well, that's an interesting question. Let's run this experiment again. So 1.159 is how long it took. Let's run it again. 1.203 seconds. That's different. We better run this again. 1.221 seconds. What is going on here? So there's a couple things going on. So first off, the difference between the Commodore 64 executing this very simple program and this machine right here executing this program is the Commodore 64 is like from the early 80s and had very limited processing power, at like only a few megahertz. And the machine that just run this program right now in less than 2 seconds, less than 1.5 seconds, is a brand new Ryzen 9 5950X. It's a lot faster. So the length of time that a job is going to run for is also dependent on the hardware on which it runs. So even if a human can't predict how long it's going to take for the thread to run, the computer itself, the computer you are running it on, it's going to take a completely different amount of time. Now there's one other interesting thing, and you just saw me run the same program back to back 3 times, and I got 3 different outputs from time. And that is because even though it appears that I am not doing anything else on this computer, we don't know what's happening underneath in the operating system. So you can actually see her time breaks it down into 3 blocks. So there's real, which is the amount of time the user would experience. The user time is how much actual time this program spent executing code on one or more CPUs. And then sys is how much time the kernel spent executing code. Now, this is the really interesting thing. You're like, wait a minute, most of the time for this program was spent in the kernel? Yes, because if you look at this program here, cout is a system call. They're expensive. The faster way to run this is to actually malloc an array on the stack that, well, not malloc, because you don't want to malloc, because that's also going to be a system call here. So you want to create an array on the stack that would fit all of the numbers, and then you want to copy all of the numbers into the array and then print the array as a string and have one system call for printing instead of a million system calls. So the reason why this program spends so much time in the kernel is because we're doing a million separate system calls. We could make it a lot faster. I'm not going to do that right now, but just for the sake of discussion. So we have a lot of different things coming into play as to why we can't really estimate how long a job is going to take to run. Number one, because we as a human don't know how long we're going to be on that website for, or playing that game, or watching that movie for. Number two, because it's going to take a different amount of time on each piece of hardware. And number three, because you have no control over what is actually happening in the operating system itself. For example, if I was doing a bunch of other things on this computer at the same time, and I mean, technically I'm streaming this in 4K at the same time, so my computer is pretty busy, but I also have like a ton of cores, so it's not really a big deal. But let's say I was... So I have a program right now that's doing analysis on, sentiment analysis on 41,000 different movie scripts. And I do that with about 15, 16 threads. And if I was running that at the same time, I would expect this would actually take a lot longer, simply because of what else was going on that computer at that time. So when it comes to scheduling, using something like knowing how long a job is going to run for doesn't really make sense, because there are many factors in how long something is going to take to run on your computer. And what's interesting is if you read a lot of papers, they'll tell you, oh, this is how long it took exactly. And those numbers are essentially meaningless, because unless you specify your exact computer specification and you mention, here's my operating system, this is what I was doing at this time, and I did 1,000 runs, and this is the average of those 1,000 runs. For any other machine or any other setup, those numbers are going to be different. So when people give you those precise numbers, it's not necessarily that meaningful. And it's interesting because you go back in computer graphics and you read papers from like years ago, and they list, this ray tracing program took 30 seconds on the following PC. And it's like, but that's a computer from 10 years ago. What am I supposed to anticipate as an expected runtime on the computer I have today? And if you want to know why do we use the big O notation, things like, oh, the runtime is O of n, why is that so important? Because that's not dependent on your computer. That's not dependent on your operating system. That is counting basic operations. And that is way more meaningful in terms of performance than saying, oh, it ran in this speed on this machine on this date. Because the next day it may not take that amount of time. Anyways, that's a long rant. Okay, so if we wanted to build a more sophisticated schedule, there's some other things we should probably take into consideration as well. So that is the concept of efficiency and implementation, because if it takes a really long time to choose which thread goes next, and I mean, you could use a machine learning to guess how long it's going to take to get that, but machine learning algorithms are not exactly fast. So we need something that's actually efficient. We want to make sure it's being fair. We want to make sure that we don't have any starvation. We want to be able to handle things like yielding and blocking. And right now we haven't even talked about that. Now in round robin and first come first serve, I think it's fairly obvious what you do. When you yield, you go to the back of the line. When you become unblocked, you go to the back of the line. But how do you do that? In shortest remaining time, how do you handle those? The other thing to consider is that we've made the assumption that every thread has an equal priority, and that is simply not the case. If you look at your computer right now, some of your threads will have a lower priority than others, and if you have a lower priority, it means, at least on a Linux-based machine, that you are getting less CPU time than other threads. We want high priority threads in general to get more CPU time or more opportunities to run. So we want to be able to actually have priority and have the scheduler obey that priority. So what I want to do now is we're going to take a quick look, very high level, at two real world scheduling algorithms that are actually used and go from there. So the first one is called Multilevel Feedback Cues. And I want to tell you this is probably the most popular scheduling algorithm used today. It is used in Windows. It is used in macOS. It was used in Solaris. It was used in the Linux kernel, but it's not anymore. But I do believe it is used in BSD still. Point is, this is very popular, and we're going to talk about it at a very high level. Know that each operating system is going to have its own very specific variation of it. So the whole point of multi-level feedback cues is we want to be very responsive to interactive threads. Now, that's going to be something that is interacting usually with the user. What does it mean to be interactive? Well, it's going to be threads that run for very short periods of time before they either terminate or they block to wait for data to arrive or user input. And we want to make sure that once they get that user input, that they are very quick to respond to the fact that they've gotten that bit of interaction from another device or from the human. But how do you know whether a thread is going to be interactive or not? Because this isn't necessarily a priority. This is like a function of how the thread is actually being used. So something like a video game. How do I know that the video game thread needs to be is going to be very interactive? And of course, video game threads are very interactive because they're constantly waiting for user input. So what we're going to do is this multi-level feedback cue is kind of designed in such a way that the interactive threads are going to make themselves known just based on the fact that interactive threads we're assuming are going to block frequently to wait for something. So we're going to subdivide, instead of having one ready queue, we're actually going to have n ready queues. And the highest priority queue will be Qn, and then we'll have, lower priority queues all the way down to the lowest priority queue, which is Q1. And for each of these queues, we actually set a separate scheduling quantum. So you've been used to the fact that there's only one scheduling quantum. Well, with multi-level feedback queues, we actually set a scheduling quantum based on the queue you come from. So if you come from Qn, that is the highest priority in this case is most interactive threads. We are assuming that you're going to run for a very short period of time, so the scheduling quantum for high priority threads is very, very small, very short. Whereas the lowest priority thread, we assume you're not interactive, and so you have a longer scheduling quantum. So what then happens is every thread is going to start out in the top of this chain of priority queues. And we always choose a thread to run from the highest priority queue that has threads in it. So everybody starts out at the top, and when you get selected to run, if the scheduling quantum expires before you terminate or block, then we don't believe you to be that high of priority. And so you get put back not on the top, on the back of QN, you're going to sift down to QN-1, which has a slightly longer scheduling quantum. And if we choose you from that queue and you preempt again, then you're going to sift down and down and down. If, however, you do block before the quantum expires, then you will go into a block state, and anyone who wakes from a block state gets dumped back up into the top one, because we want to make sure that when you get the data, you have a high chance of actually using that information right away. So this may seem a little confusing. Let's look at this example with just like 3 threads, or not 3 threads, 3 queues. So this is a 3 queue system. So we've got Q3 is the highest priority, Q2 is the middle, and Q1 is the lowest priority. And what's going to happen is everybody starts in Q3. We are always choosing a thread to run from the highest priority queue that has threads. So that's always going to be Q3. If there's no threads in Q3, then and only then do we look at Q2. If there's no threads in 3 or 2, then we look at the bottom one, Q1. So let's suppose someone is in Q3, they get scheduled to run. If they get preempted, they go down in priority, and then we would take another Q3 if one is available. So you're going to sift down as you get preempted. Once you get to the bottom, since there's nothing lower, preemption's just going to keep feeding you back into the lowest priority. If any of these threads at any of these points fall asleep because they're blocking to wait for something, when they wake up, they will automatically go into the top high priority queue. Okay, so that's kind of how this is running. And so you might be wondering, well, how many levels does Windows use for it? So it's actually changed a fair bit since I last used Windows on a daily basis. I don't really use it much anymore. I think right now Windows might have 10 levels, but the last time I actually looked into this, I'm going to say there was maybe 5 or 6. And then Solaris, I think Solaris has 5. Let me think about that. 5 or 6. Yeah, it was 6 for Solaris. And so Solaris had 6 levels, and the scheduling quantum for the highest priority queue is 40 milliseconds, and then the scheduling priority for the lowest priority queue was 200 milliseconds. Lots of different implementations. So let's do a quick example on how this actually runs. So let's suppose we have 2 threads. They are brand new threads, so they're going to start in Q3 because we know nothing about them. And what's going to happen then is it's time to choose a thread to run. And I see that I have threads in my highest priority queue. Therefore, I'm going to choose T1, which is at the front of Q3. So T1 gets to run. T1 gets preempted, and so it goes down into ready Q2. Because it's not that interactive, it got preempted. And when it got preempted, we ended up choosing T2 from Q3 because it has a higher priority than T1. So now T2 gets to run. If while T2 is running, a new thread arrives, because it is a new thread, it goes into the highest priority queue. And since T2, the running thread, and T3, the new thread, have the same priority, life's going to go on. Nothing's going to happen. T2 keeps running. T3 is going to wait. If T2 terminates, then we have to choose between T3 that was in ready Q3 or T1 that was in ready Q2. We always choose from the queue that has the highest priority. So since Q3 had something in it, we're going to take T3. Now, T3 blocks. So when it blocked, Q3 was empty, and so we finally got to pick something from Q2, and so T1 finally got to run again. If T1 gets preempted, it's going to sift down, and it's going to go down into ready Q1, and then since there's nothing in Q3 and there's nothing in Q2, we finally get to choose something from Q1, and so finally T1 gets to run again. Now, while T1 is running, let's say T1 made a resource available for T3. So T3 is going to jump from the blocked state into ready Q3, so the highest priority. And now we have a thread available that is a higher priority than the one that was running. And so this can actually preempt the running thread if it is of a lower priority, such that now T3 is going to be able to run. So that's an interesting property of multi-level feedback queues. And you don't have to implement this feature, but it is a common implemented feature, is that when the running thread has a lower priority than the newly arrived thread in the system, the running thread will get booted off in favor of running the new thread. And this is advantageous because the lower priority threads are going to be allowed to run for much longer, which would force the higher priority threads to wait longer before they get the CPU. So by allowing the higher priority threads to boot the lower ones off the CPU, we're going to be more responsive to those high priority threads that are more interactive. So T3 is going to end up running. Now, there's some problems with what I've said here. What if we have a never-ending stream of high priority threads in the system and they never get preempted? What happens to T1 all the way at the bottom? Will it ever run again? And the answer is no. Actually, this multi-level feedback queue implementation, as I've shown you here, actually has a problem of starvation. But never worry, it's actually quite easy to fix. So what you do to solve the starvation problem with multi-level feedback queues, where threads end up sifting down and they stay down there and never get to run because there's a whole bunch of stuff up here, is you periodically take every thread in the system and you push it all back up to the top. Sift it down, push it back up to the top. Sift it down, push it back up to the top. And if you're wondering how often does that actually happen, so Solaris was doing it once per second. So every second, it took every thread in the entire system and put them back up into the highest priority queue so that they could sift back down again. So that is how you prevent starvation from multi-level feedback queues. And there's so many different variations, like you can allow users to adjust the priorities of things such that, certain threads never go below a certain level. And there's lots of interesting variations for multi-level feedback queues. And they're super popular, so it's important to know. Now, what does our beloved Linux kernel do? So they actually don't use multi-level feedback queues anymore. They do something called the completely fair scheduler. And this is very different. So instead of having multiple different scheduling quantums, what they do instead is they are going to have a single scheduling quantum, but every thread is assigned a weight. And the idea is that the weight represents the share of the processor time you're going to get. So you get your share of the CPU time is proportional to your weight. So a higher weight thread is going to get more CPU time than a lower weight thread. Seems fairly straightforward. And how they actually manage this is they keep track of a couple different metrics for each of the threads. They keep track of one thing called the virtual runtime. And they keep also track of something called the actual runtime. Now, the actual runtime is how long a thread has actually run on the CPU for. So let's open up this lovely program again. And what we're going to do is scroll. Oh, so I have to add a new page. Page after? I don't know. I've never really used this program before. So what we've got... So we're going to compute the virtual runtime as a function of actual runtime and the weights. So we have the virtual runtime is equal to the actual runtime, so how long a thread has actually run on the CPU, multiplied by the sum of, I think I have it there on there, so all thread weights divided by your weight. So this is all thread weights. So it's the total weight of all threads And the one on the bottom is going to be your weight. That's not too bad, right? So for example, if your actual runtime, let's say, is 5, and let's say that the sum of all thread weights in the system is 100, and your weight, let's say, is 25, then your virtual runtime that we're going to compute for you is equal to 5 times 100 over 25. So that's going to be 5 times 4, so 20. Now, how is this relevant to the scheduling algorithm? Well, what's going to happen is the completely first scheduler always chooses the thread to go that has the lowest virtual runtime. And what's interesting is that higher weight threads, their virtual runtime is going to advance more slowly than a low weight thread. So for example, if my weight was, instead of 25, let's say my weight was 50, then my virtual runtime for that oh wait, that's a higher weight. We can do it with higher weight. Let's say we had a higher weight, so you can see that the higher your weight is, the lower your virtual runtime is. So that would be 5 times 2, so we end up with 10. So the higher your weight is, the lower your virtual runtime is going to be, so the more likely it is that you are going to get to go next. And you might be like, well, doesn't that mean that the high weight threads are always getting an opportunity to go? Yes, but there will become a point where the virtual runtime of a high weight thread is now bigger than the virtual runtime of a low weight thread. So there will be this point where we cross a threshold, and that threshold we are crossing is this thread has now crossed the threshold of its fair share of the CPU time proportional to its weight. And when we cross that threshold, then one of the lower priority threads actually gets to go. So it does work out, and it's fairly straightforward to do. So there's a little bit of an example on the next slide just to show you. So we're assuming that the sum of all weight threads in the system is 50 and the scheduling quantum is 5. So we start at time t, and we've got to choose between threads 1, 2, and 3 with the following weights, 25, 20, and 5. And they all have the same actual runtime. So we would compute then the virtual runtime for each of those threads. So we've got 10, 12.5, and 50. So we'd end up choosing, in this case, thread 1. And yes, there's a typo there, I'm aware. And so we're going to choose the first thread. And so it is going to get to run. So its runtime, actual runtime, is going to advance by 5 units. And now we see in the next time unit, so at time t plus 5, we compute the virtual runtimes again, and we see that T1, even though it is the higher weight, it has crossed the threshold of its fair share of the CPU's time. So it ends up with a virtual runtime of 20, whereas thread 2, whose weight is almost the same as the thread 1, it is only 12.5, and so it's going to get to go next. Pretty neat, right? Now, there's some interesting problems that kind of arise with the completely fair scheduler. One of them being, what do you do when a thread is new? Because when a thread is new, its actual runtime is 0. So it's going to be like, oh, brand new thread, 0, 0, we better run it. And then there's a chance that that new thread, because all the other threads are really old, their actual runtimes will be high. And so the new thread will get an unfair initial balance of CPU time, starving out potential other threads. So what they end up doing in this situation is when a thread arrives, you choose its initial runtime to be somewhere between the minimum on the system right now and the maximum on the system right now. And the same is true if you've been blocked for a really long time. You might get an unfair burst of CPU time. So again, when you become unblocked, we may have to artificially choose a new runtime for you based on the current system minimum and the maximum in the system, just so that you don't get any unfair bursty behavior, because unfair bursts can actually starve out everybody else, and we don't want that to happen. That's the completely fair scheduler in a nutshell. There's actually a lot more to that. And a lot of people ask me, why do you have to compute the weight ratio every time? And that's because the threads in the system is changing all the time. So you have to actually keep track of that. There's actually a paper on this. Maybe I should make a note and post it if you're interested. It's not a bad read. if I remember correctly, and I haven't read this paper in probably 10 years, it uses red-black trees, which used to be a topic in CS240 but isn't anymore. For the record, a red-black tree is a balanced tree. Yeah. All right. So one last topic in scheduling before we go here. And I don't want to take too much time, more of your time here. But how do you actually handle scheduling when you have a multi-core processor? So the machine I have sitting in front of me is a multi-core processor. It has 16 cores, and each core can technically run 2 threads. So that's like 32 threads. How do I handle that, scheduling on that? Well, there's 2 kind of schools of approach that you could do. So you could have a per core ready queue. So 1 ready queue for each and every core. Or you could have a shared ready queue that all of the cores are going to pick from when there is preemption or when a core needs a thread. So I want to talk about the shared implementation first. So it's very easy to obviously implement this, but we do have one interesting problem, and that is that only 1 core can technically get a new thread at a time, because otherwise you're going to have a race condition over the scheduling, the actual ready queue. So what ends up happening is, while this is very simple to implement, we end up with a scalability problem because we get contention for this shared resource that is the shared ready queue. So that's not so advantageous. Now, for the system sitting in front of you, it's probably not a huge deal. I mean, I wouldn't want this implementation for this Ryzen chip, but, you know, for my I got a Surface 3 sitting over here. It's fine for that because it's never doing anything much. It doesn't have that many cores. I think it has 4. It's an i7, but it's like an i7 from 2014? Jeez, it's old. I don't remember how old it is. Anyways. So, I mean, for something like this older machine with fewer cores, it's not going to be a big deal because there's not that many cores trying to all share that shared ready queue. But on this machine, this Ryzen machine, now we're talking there's a lot more cores. And if you think about, keep expanding this, you know, this is just a consumer grade desktop processor. What about those lovely Threadrippers that are like 64 cores? What about, you know, an actual data farm? What about an actual like render farm? So like I've been in Pixar's render farm. It's a thing of beauty. I mean, it's really loud, but it's also really awesome. And it's this huge room of just servers. And how many processors are there all vying for access to this one shared ready queue? That doesn't make sense because there's going to be contention. While one of those 10,000 cores is waiting for something, the other is acquiring a new thread, the other 9,999 would have to wait. And that's not what we want. We don't want that at all. One of the other interesting issues that comes up is every time a thread runs, it may run on a different core. Now, that may not seem like a big problem, but if we want to talk about the concept of cache affinity, it is a problem. We do want cache affinity. So cache affinity is the idea of you ran once, you filled the cache up with a bunch of data that belonged to you, and then we didn't clear the cache out. And it would be really nice if the next time you ran on the same core such that there might still be some things left over in the cache that would help give you a little boost the next time you get to run. The problem with the shared ready queue is that you don't really get any guarantees of cache affinity because you wouldn't be running on the same core each time. So it doesn't scale, no cache affinity. So you may be like, well, then the obvious answer must be 1 ready queue per core. But actually, if you look at this picture, it actually illustrates one of the biggest problems. So we don't have contention for shared resources here because there is no shared resource. Each core has its own queue. But it's not very fair. We actually end up with a load balancing problem. So the problem is, let's say for an hour of time, this one little thread here gets the entire core to itself for an entire hour. Whereas these 4 threads here, they only get a quarter of the time, and these 5 threads only get a fifth of the time. So you end up with this load balancing problem, and you can, in early versions of Windows, when multi-core became a thing, you would actually see this. They didn't do load balancing across the cores very well. So even when you have lots of tasks running, you'd see one of your cores at 100% and the other 3 at 0. And that's a problem, because that means that one core, you're not getting the performance that you expect out of your hardware. So what you need to do is you need to do something called load balancing. So this is really good. It's very scalable. The other thing I want to say about this method is that it also has great cache affinity, because the threads that are on this core are presumably always going to be running on this core. So you have a greater chance of getting cache affinity. The load balancing is the downside. Now, there are ways to mitigate the load balancing issue, but they come at the price of the cache affinity. So one of the things that you could do is new threads, always put them on the core that has the lowest balance or the fewest threads to work with. But what if you don't have a lot of new threads? What if you're just dealing with the existing system and it's out of balance? So what would then happen is periodically you rebalance this by taking some threads from here and pushing them on from the high load cores and pushing them onto the low load cores. Balances the load. Downside is you're going to lose some of that cache affinity when you do this. How do we actually want to do things today? Obviously, we want to do this per core model because it's much more scalable, and we'll take the hit from the load balancing. All right, so that is actually it for scheduling. It's a pretty short topic. Yes, I know there's 2 more slides. It's just text about the things I just talked about, and I'm not really going to sit here and read slides to you. So that is everything for today. So in our next episode, which will be on Thursday, we're going to start another new topic, which will be devices and I/O. So we're going to start looking at how does your operating system actually communicate with the hardware itself? Because, you need to take input from a keyboard and a mouse, and you need to be able to send packets over a network. How does that actually work? How does the kernel actually interact with the hardware? So that will be in Thursday's episode. So we will see you then. And I hope you stay cool today, because it is pretty hot outside.